Buenas noches, good evening, everybody. Welcome to day 2 on week 5 of the semester. Today, we are going to be talking about the topics for chapter 5, which is where we learn about chemical reactions. When it comes to chemical reactions, this is not a foreign topic to you guys, because we actually learned about chemical reactions when we were talking about the changes that matter undergoes. So if you recall, we learned that matter can undergo physical changes and chemical changes. And chemical reactions are going to be those chemical changes that matter can undergo. And remember that in a chemical reaction, the substance that you start with is not the substance that you end with. Because in the process, since we have the creation of a brand new substance, then understand that that brand new substance that is going to have the same elements, because that's the only thing that is not going to change. Maybe the number is going to be a little bit different, but understand that that brand new substance that is created is going to have its own physical properties and its own chemical properties. Now, when it comes to reactions, understand that there are 3 conditions for a reaction to occur, okay? And the 3 conditions are, number 1, collisions. So what do I mean by collisions? Well, the reactants have to hit each other, in other words, collide. So what that means essentially is that the reactants need to meet. So what are the reactants? Those are going to be the substances that have to meet each other in a reaction. Now, the reactants, or the substances that are going to undergo this chemical change, need to not only meet, but they need to meet in the correct orientation. They need to align properly in order to break the bonds that are necessary and also form the new bonds that are necessary for producing those new substances. Now, understand that all of these processes need to happen in terms of a particular type of energy in which we called activation energy, okay? And when we look at activation energy is going to be the energy specifically, when we look at this chart, that the reactants have to achieve, okay? So from reactants to the top of the hill, in order for them then to reach the product. So activation energy, again, is going to be the energy that starting from the energy of the reactants to the top of the hill. All of that is activation energy. Once they are on top of the hill, then as you can see in this process, then the energy is going to be reducing, or getting smaller, I should say, getting smaller, all the way until we make products. So in this particular reaction, the product that it is produced is going to be lower energy. That's why we see it here, compared to the energy of the reactants. So in this process, we can see that energy is being released. This illustration that you guys are seeing is what is called an energy diagram. And an energy diagram just illustrates the progress that a reaction undergoes, correlating how the reaction is progressed compared to the energy that is consumed versus the one that it is released. That's what an energy diagram is. Now, whenever we have a reaction, we always have to consider what are the thermodynamics and what are the kinetics of the reactions. As you can see, thermodynamics is going to refer to the heat and energy exchange in a chemical reaction. So when we're looking at thermodynamics for a particular reaction, understand that what we're looking at is going to be the potential energy in the bonds of the reactants which are the substances that are going to interact with one another, versus the products. And the products are going to be the substances that are created. Thermodynamics can also give us an insight about spontaneity. And spontaneity basically tells us how likely is this reaction to happen, okay? Overall, if you input energy or if energy needs to be released from the system. But I am not going to discuss specifically the whole idea of spontaneity. We also have the kinetics of a chemical reaction. And when it comes to the kinetics of a chemical reaction, understand that that refers to the pace, in other words, the rate of a chemical reaction, okay? So when we're looking specifically about the kinetics of the reaction, understand that we're looking at the intermediate steps, meaning the bonds that are broken versus the bonds that are made on the way for those reactants to turn into products. That's why whenever we talk about kinetics for a reaction, we talk about the speed of the reaction, because you are considering this reactant create this intermediate, meaning what has been broken, what has been made in order to get to that product, and then how fast do we get there. So now we are going to focus into section 5.1, which is where we look specifically at thermodynamics, okay? So as you can see, when it comes to thermodynamics, we need to consider that reactions can happen in one of two ways. Reactions can be exothermic, which is the illustration in the notes that we have on the left, or the reaction can happen under endothermic conditions, or in other words, the reaction can be endothermic. So now let's focus on an exothermic reaction, okay, which is the image on the left. If we have an exothermic reaction, understand that the term exothermic means that exo refers to exit, thermic is going to be the heat that is generated. So in an exothermic reaction, as you can see on the bullet points, heat is released during the reaction, okay? Now, when we look at what is the potential energy for the reactants versus the products, as we can see in the diagram, we can see that specifically the products are going to be lower in energy compared to the reactants. Because if we think about, how we draw the different axes, as you can see, the x-axis is going to be the reaction progress. The y-axis, which is the one that is pointing up, is increasing in energy. So since the y-axis tells you that all of those values are going to be increasing in energy, we can see that for an exothermic reaction, the energy of the products is less than the energy of the reactants. Additionally, it is understood that in an exothermic reaction, because energy is being released, in other words, heat is being released, then heat is a product, okay? And basically, remember, if it's a product, this is going to be what is generated during that chemical change. So we can see units of kilocalories. This is a unit for heat. And then we see it on the right side of the arrow. So that means that it is a product. So if I give you guys an insight into this, let me just do some labeling. This part of the reaction is going to be where the reactants are. On the right side of the arrow, that's where the products are. So that's why, since in an exothermic process, the heat is generated, then that means that heat is a product, okay? Now, when it comes to endothermic reactions, they can also happen. So when it comes to an endothermic reaction, understand that heat is absorbed. Now, you may have experienced already an endothermic reaction without knowing it. Put a 1 in the chat if you have ever had to utilize a cold pack. You know those packages where you have to kind of like crack them, like whatever is in there? There you go. Many of you guys have had to use a cold pack. Great. So the chemicals that are inside the cold pack actually generate an endothermic reaction. And in an endothermic reaction, heat is going to be absorbed from the environment, okay? And as a result, most endothermic reactions are going to be getting cooler over time. And again, the utilizing a cold pack is an illustration of an endothermic reaction. Now, when we look at the energy diagram for an endothermic reaction, you can see that specifically the energy of the products, the potential energy of the products is going to be higher than the energy for the reactants, okay? Now, because heat is being absorbed, okay, from the environment, we see that in a chemical reaction, that heat is going to be written in the reactant side. Remember, the left of the arrow is where the reactants are. The right of the arrow is going to be where the products are. So that's why we see 43.3 kilocalories in this reaction, illustrating that since heat has been added in the reactants, this is an endothermic process. Questions about endothermic versus exothermic reactions? Now let's look at an application for thermodynamics. And specifically here, we're going to be looking at an exothermic reaction. So calorimetry is actually an application of thermodynamics. What is calorimetry? Calorimetry is going to be specifically where we look at if you have a substance and heat is released, we're going to be observing how that can change the temperature of water. So because it's going to transfer some of its energy into the water, okay? So when we're looking at calorimetry, understand that a calorimeter is the instrument that is utilized to measure this heat transfer that is going to occur in this exothermic reaction. Now, what is a calorimeter? You can see that in the right side of the slide, we have an image of specifically the calorimeter. Give me one moment. One moment, you guys. Okay, continuing on. So this is the basic setup for a calorimeter. So a calorimeter specifically is the instrument that it is utilized in order to understand the energy that can be released from a food sample. So when we look at this setup, you guys can see specifically how we have a food sample that is placed inside a chamber. And this chamber has oxygen. So what's going to happen overall at this compartment inside of the calorimeter is that this food sample specifically is going to undergo a combustion reaction. We're going to learn in a few moments that a combustion reaction is a particular reaction that actually releases heat. We can see it illustrated here in the form of this flame. Now, because this exothermic reaction is going to release heat, the heat is going to be transferred onto the water. As you can see, here we have a thermometer. And that thermometer is going to measure the temperature change from start and after the combustion has happened in food, okay? Now, as you can see, a calorimeter, you guys, is what it is utilized to calculate the energy value in food. So, whenever we have a nutrition facts label, a calorimeter is what's utilized in order to know what are the calories that we have in particular foods, okay? Now, understand that these energy calories that we are obtaining from food specifically are what we call nutritional calories. And we know that this is a nutritional calorie because you have a capital C specifically written in the unit for energy, okay? Now, when it comes to one nutritional calorie and an energy unit a unit for energy, understand that one nutritional calorie equals 1,000 calories. So I don't want you guys to be confused about, okay, what is calories? When it comes to units for energy, we can have the units of calories, we can have nutritional calories, which is a capital C. We can also have another unit that is called joules. Okay, those are the basic units. It's kind of like the meters for length or the liters for volume. When it comes to energy, we're going to use the calories, which is the first bullet point, or joules. Nutritional calories, as you can see, is correlated to the first unit of energy because one nutritional calorie equals 1,000 energy calories, okay? Since the prefix 100, we can exchange it for kilo. One nutritional calorie basically means that that is going to be 1 kilocalorie of energy. Now, let's explore how this exothermic reaction that I mentioned to you guys, that it is measured via a calorimeter, really leads to understand how many nutritional calories are in a food sample. So for example, it is very important that you guys know what are going to be the energy that is produced per gram for each of the following biomolecules. So whenever we have a food, the carbohydrates, okay? Put a 2 in the chat if you have heard that word before, carbohydrates. For those of you, oh, great, there's a number of you that have heard that word. What does that mean? Whenever we think carbohydrates, what do we mean? What is another word for carbohydrates? Starts with an S. Starches, sugar, exactly. So it's going to be specifically sugars. Then we have fat, and we're familiar with fat, like in everyday life, like the oils that you may have at home are an example of fat. And then lastly, we have protein, okay? Why is this important? When it comes to a food sample, only those 3 biomolecules are the ones that are going to be through biochemical pathways that we're going to see in chapter 12, that's how energy is being generated, okay, in the body. So let's look at the following nutrition facts label, okay? As you can see, the serving size for this nutrition facts establishes that you can eat 14 crackers, meaning that on average, that's going to be weighing 31 grams. But then you can see that we have the total fat, the total carbohydrate, and the total protein. There's other important information that is in this food label. You can see that there's saturated fat. In saturated fat, because we just finished talking about hydrocarbons, will be fats that their carbons are single bonded to hydrogens and single bonded to other carbons. As you can see, you're going to have unsaturated fats. And unsaturated fats are going to have one or more carbon-carbon double bonds, okay? Look, trans fat. We talked about trans on last class. So remember, trans is going to be that conformation for an alkene in which the groups are going to be pointing opposite from each other. So some of this terminology is something that you guys have heard before. Now, even though there's so much information here, as you can see, the fiber, the vitamin A, the calcium, the iron that these crackers have, the only information that you're going to utilize, which is correlated, okay, to the calories here, is going to be the fat, the carbohydrate, and the protein, okay? And let me illustrate how those three lead to the 120 nutritional calories that you see on the label. So this is what you guys do in terms of the math. You're going to write how much fat, how many carbs, and protein you have on your food label. Okay? So as you can see, for fat, we have 4 grams. For carbs, we have 19 grams. For proteins, we have 2 grams. Okay? Now, I go to this table at the bottom of the slide, and I can see, I just move this. Down here. We can see that every gram of fat is going to contribute to the energy that can be released in the body, 9 kilocalories. In other words, 9 nutritional calories. So that means that the fat in these crackers are going to contribute 36 nutritional calories. Remember, nutritional calories and kilocalories is going to be the same thing. When it comes to the carbs, per every gram of carb, we specifically are going to have 4 nutritional calories being produced from the carbs in this food. So how many nutritional calories can we get from those 19 grams of carb? Do the math. Let's put it in the chat. Great, 76. Lastly, per gram of protein, we also produce 4 nutritional calories. So how many calories of energy is the protein in these crackers providing the body? Great job, you guys. 8 nutritional calories. So then we're going to add these 3 numbers. 36 plus 76 plus 8 equals how much? Great job. 120 nutritional calories, which is the number that we see here. Okay. Now, I want to do one exercise with you guys. So in my Costco runs, I noticed that they were advertising these, okay? Put a 1 in the chat if you have seen these. Now, you don't have to confess. You don't have to tell me, oh, yeah, I tried them. I have them at home, okay? But if you've seen them around, good. As you can see, these are Nurture Valley. Again, I am not promoted by them. I am not getting any commission from them. I just want to have a teaching moment about these things. You can see clearly the label. It says that these are protein chewing bars, okay? You can see that it per serving, okay, which is 1 bar, these provide 190 nutritional calories. Okay, so when I ask you what is the serving size in grams, we can look at the label and say, well, my bar should weigh 40 grams. Put a 2 in the chat if you see where I got that 40. I will underline it so it's more clear for those students that missed it. That's where those 40 comes from. Now, I just show you guys how to determine the nutritional calories in a food by specifically looking at the fat, which this is 12 grams, versus the carbohydrate, which this is 14 grams, versus the protein, which is 10 grams, okay? So I want you guys, take a moment and with the numbers that you have on the table for fat, carbohydrate, and protein, I want you guys to calculate to see if this 190 is correct. So take a moment, let's do the second bullet point. Let's calculate it out. And whenever you guys do your calculation, let's put in the chat what you find. In the meantime, I'm going to be writing the notes for those students that need to see the calculation numbers. So I'm going to write for the fat, it's going to be times 12. For the protein is times 10. For the carbohydrate is times 14. Let me highlight this for you guys. So this comes from this. This comes from this. And then this comes from this. Ooh, I'm seeing those numbers in the chat. Let me just finish the numbers on my end. But I see what you guys are seeing. This is 56 nutritional calories. This is 108 nutritional calories. This is 40 nutritional calories. Yep, I got the same thing, you guys. 204 nutritional calories. Put a 1 in the chat if you knew that nutritional labels at times, I'm not saying always, at times, they don't tell you the correct number of nutritional calories in food. Put a 1 in the chat if you knew that that's true. Oh, there you go. A lot of people know. But it is interesting. There is no regulation when it comes to this. Even if I try to claim like, oh, it's sick figs, like there's no way, 190 versus 204. There's no explanation for this. Don't try to claim that, oh, it's because of the fiber. The fiber. Fiber does not produce energy. So we cannot even claim that fiber is doing something here. For me, this is just very interesting. Now, from the label, right? Specifically, if you are trying to do, good health choices for you, you're trying to do some modifications for yourself, just because you're trying to be healthy, you'll be like, hey, this is a protein bar. It is at Costco. Let me get it. Let's answer the third bullet point, which is what's the major source of nutritional calories here? So in order to answer this question, what I want you guys to do is to compare 56 versus 108 versus 40. So when it comes to this, great job. Here, fat is the major source of nutritional calories. But if you think about it, right? Again, I'm not trying to throw shade. I'm just illustrating how at times we really have to be careful and we have to look at food labels, because it is interesting to see that even though, from advertisement and because of the labels that we see on the box, it says protein, right? And indeed, this have protein, like it does. We're not claiming that it doesn't, which is great. But the major source of nutritional calories here is going to be fat, not necessarily the protein, which you see in big letters. Does it have protein? Yes. But if we carefully study the nutrition facts of things, then we have to add, pay attention to the numbers and say like, okay, is this really a good food choice for what I'm trying to accomplish, with my health? So be careful whenever you have, food labels out there that you're trying to explore, okay? And understand that sometimes these labels that you see on the packaging give you messages that you need to look further into the nutrition facts. Any questions when it comes to given a food label, trying to calculate the nutritional calories that you have present in the food? Awesome. Then let's move on to the next topic, which is chemical reactions kinetics. As I mentioned to you guys, whenever we're thinking about kinetics, we need to think about the rate of the reaction. And the reaction rate is going to be a measure of the change in the concentration, okay, for the reactants or the products that we have per unit time, okay? So there's certain things, there's certain factors that can increase the speed of the reaction, meaning that trajectory from reactants to products. These are, as you can see, an increase in the reactant concentration. And the reason why the reactant concentration can affect the kinetics of the reaction. Another way, increase the rate of the reaction is because now if you have more reactants, they can collide more. If you increase the temperature of a reaction, as you can see, you're going to have more collisions, and those collisions are going to have activation energy that is going to take those reactants to products. Now, lastly, you see that the addition of catalyst can also increase the rate of the reaction. So you may be wondering, what's a catalyst? Well, a catalyst is going to be a chemical compound that is going to increase the rate of the reaction, but very different from the first two factors. When it comes to a catalyst, how a catalyst increases the rate of the reaction, the speed at which we go from reactant to product, is going to be specifically by lowering the activation energy. So if we see the energy diagram that is given right here, and this is where my reactant started, and when there's no catalyst, you see that there's this activation energy before we reach product. Once you add the catalyst, as you can see, the energy of the reactant does not change. All we see is that this hill is going to be smaller as we go into products. So as it says here in the fourth bullet point, adding a catalyst to a reaction, again, is going to increase the rate, but understand that it's not going to change the energy that is stored in those substances that are called reactants, and it's not going to change the energy stored, in other words, the potential energy in the products. The only way that this catalyst is going to be increasing the rate of the reaction is specifically by lowering the energy of activation. Understand that a catalyst is something that it is used, meaning that it is interacting with the molecules in the reaction, but is not going to disappear. So it's going to participate in the reaction, but it's not used up. What that means is that the catalyst is regenerated or is produced again at the end of the reaction. Catalysts are very important in biochemistry. We're going to see specifically as we progress this semester towards the end of the semester, when we talk about specifically biochemistry, that most of the reactions that happen in our body are thanks to catalysts. Because in the time frame that reactions need to happen, we need catalysts in order for the reactions in our body to progress. Any questions about kinetics, the factors that increase reaction rate, or the concept of a catalyst? Put a 1 in the chat if you're ready for the next section. Great. So let's talk about an overview of chemical reactions. We have mentioned a little bit of chemical reactions, okay? And now let's understand that when it comes to chemical reactions, as I mentioned in the beginning of today's lecture, these are going to be chemical changes in which one substance turns into another, okay? Now, when it comes to chemical reactions, understand that there's going to be different indicators that will let us know that a reaction has really happened. So, a color change, meaning when you add the two substances, and you can see in the image here, we see smoke. Most likely, it could be that this reaction releases heat. That's why we see the smoke. But more importantly, in terms of the color change, we can see that fuchsia being generated. That may mean that the new substance that is created will have a particular color, okay? Another indication that a chemical reaction has happened is the formation of a solid, okay? So if you combine two substances, but then one of the products that is produced is a solid, okay, then we can see it here in the reaction. And because solids at times are heavier than the liquid, that's why you see it going to the bottom. The formation of a solid in chemistry is called a precipitate. So whenever we have a precipitation reaction, it's because we're going to have some of this solid form, okay? Now, we also can have the formation of a gas. So sometimes you have chemical reactions that when you combine two substances, the new substances that are formed could be in gas form. And if there's a liquid present, it's going to start bubbling because the gas that is forming is trying to escape the liquid. The emission of light illustrates that there's a chemical reaction. So for example, when you guys, if you have played with or you have ever had a glow stick, you have to crack the glow stick in order to produce the glow. That is a chemical reaction. And lastly, the emission of heat or the absorption of heat can also indicate that a chemical reaction has happened. Now, how do we write chemical reactions? Well, we write them in the form of a chemical equation. There are some important symbols that we need to know when it comes to chemical equations. As you can see, and I expressed to you guys a few moments ago, all of the substances that are to the left of the arrow are called reactants, and you can have one or you can have more than one. Anything to the right of the arrow is called a product. You can form one or you can form multiple. It depends on the type of reaction. If you have more than one, it doesn't matter if it's the reactant or the product, we are going to separate them by a plus sign. The arrow is what's going to represent how the reactants react to form product. Now, if that arrow has that triangle on top, which this is a symbol delta, that represents that your reactants were heated during the reaction. Lastly, you can even incorporate the state of matter for the substances in your reaction. So all of these labels for states of matter are placed at the bottom right corner of the chemical formula. For the molecule that we're talking about. So as you can see, S is if your substance is solid, L is if your substance is liquid, okay? In terms of reactions, water is the only thing that we consider liquid. G is going to be for gas, and then we have the label aqueous. What is an aqueous reaction? This is when we have an ionic compound that is soluble in water, dissolved in water. So that's what makes it aqueous. Now, there are different types of chemical reactions, and this is a general summary because I want you guys to be able to identify the different types of chemical reactions, okay? So there are many types of reactions that are introduced to you guys in chapter 5, but this is the first set, okay? So reactions can be classified as combination or synthesis reaction. When we have a combination of or synthesis reactions, you can see that specifically we have two or more reactants that combine to make a single product. So let's say that letter A is one reactant, letter B is another reactant. In the product, you're going to see that both of them combine and make a single product. In a few moments, we are going to practice to identify the different types of reaction. The second type of reaction that we have here is decomposition. In a decomposition reaction, what we have is that we have a reactant that is going to split, okay, or create two or more products. So let's say that you have that single reactant that is A and B, okay? It doesn't need to be 2 units. It could be many more atoms, but this is just a generic illustration. And then in the product, you can see that it produced just A and just B. Then we have single replacement reactions. In a single replacement reaction, we're going to have one element, which is here, replace another element, okay, in a compound. So as you can see here, let's say that there's substance A that is interacting with substance B and C. You can see that A took the place of B and it replaced B from the original compound. When it comes to double replacement reactions, understand that in double replacement reactions, they are specifically going to switch partners, okay? And in previous chapters, specifically in chapter 3, we learned about ionic compounds, okay? So what are the 2 types of ions that any ionic compound has? What is the name that we use for a positive ion? Let's put it in the chat. What is the name? Thank you, Katie. Cation. What is the name that we use for a negative ion? Great job. Thank you, guys. Anion. So what happens in a double replacement reaction, because these are going to be aqueous ionic compounds, it's just that the assumption is going to be that A is going to be the cation in that first compound, B is the anion. In the next compound, C is the cation, D is the anion. So in a double replacement reaction, what we see overall is the switch of partners. In the switch of partners, what we observe is that cation A is going to now be with letter D. That's where AD comes from. Because remember that we always write ionic compounds plus, minus. The second compound is going to be where you take the cation of the second and you pair with the anion of the first. So as you can see, that is going to make compound C and B. Why is C before B? Because remember, C is a cation, B is an anion, and in ionic compounds, specifically, we always write cation first, followed by anion. Lastly, we have a combustion reaction. When it comes to a combustion reaction, understand that combustion reactions, let me give you guys a definition. A combustion reaction, by definition, is any substance that reacts with molecular oxygen. What is the chemical formula for molecular oxygen? You have it there, but let me see that you guys know what is molecular oxygen. What is molecular oxygen? It's not just the letter O. What is the chemical formula for molecular oxygen? Let's put it in the chat. Anyone? Molecular oxygen. Thank you, Elizabeth. O2. Okay, right here. So if you have any substance interacting with O2, that's going to be a combustion reaction. Note, if the reactant that is undergoing a combustion reaction RxN is my shorthand for reaction, has carbons and hydrogens, as you guys see in CH4, then the products are CO2, water, and energy. Do not assume that whenever you see CO2, water, and energy, that specifically is going to be a combustion reaction. Not necessarily. You need to look at the reaction overall. So now we are going to practice how to identify these different types of chemical reactions, okay? By giving you guys specific examples. Put a 1 in the chat if you're ready to practice. Awesome. Now, let's look at these molecules. So I'm going to do number 1 through 4 with you guys, so you guys know how to identify these, okay? Let me just zoom in. Let's look at the first molecule, okay? Let's look at what's happening to the atoms. We have HNO3, and then we have nickel. In the product, I see that now my nickel is where hydrogen used to be, and it's paired with the NO3, and now hydrogen is by itself. So nickel took the place of hydrogen in the first compound. So that means that this is a single replacement reaction. Again, I can see that nickel now is where hydrogen used to be. Hydrogen is by itself. That's why it's single replacement. Reaction number 2. I see one molecule. One molecule is forming 1, 2, 3 substances in the product. Out of the different types of reaction, this is a decomposition reaction. Because remember that in a decomposition reaction, we go from a single reactant to multiple products. Put a 2 in the chat if so far you understand the classification for 1 and the classification for 2. There's 3 people. There's 12 of you. Okay, we're gonna get the hang of it, okay? Let's look at number 3. I know that you guys got this. We have one substance reacting with another substance and making a single product. So I have 2 substances that they came together and made a single product. What kind of reaction is that, you guys? Let's put it in the chat. Great job. This is a combination or synthesis reaction. Now, because I have nitrogen reacting with O2, what is another classification that we can give this reaction? Thank you, Vanessa. Combustion. Okay, put a 3 in the chat if the classification for 3 makes sense. Excellent. Let's move on to number 4. In number 4, I have KOH, and I have H2CO3, and I have water, and I have K2CO3. How do I justify this? Well, let's look closely at what's happening. I have KOH, okay? Is KOH an ionic compound? Yes or no? KOH. I know this was in the first exam, but we cannot forget about that information. Remember that even though the exams are not technically cumulative, you cannot forget about the concepts of the first exam. Is KOH ionic? Yes or no? Thank you, Kiyomi. One person says yes. Guadalupe says yes. What happened to the other 12 people? I got 10 people that are like, oh, wait. Good. Thank you for putting those yeses, even if you don't understand why it is a yes. Let me explain to you why it's a yes. So in the first exam, we learned that an ionic compound is going to have a metal and a non-metal. This is a metal. Potassium is a metal. Hydroxide is a group of non-metals because it's a polyatomic ion. Okay. So when we look at this reaction, look, we have potassium. Is potassium a cation or an anion? Put C or A in the chat. Is potassium a cation or an anion? C for cation, A for anion. Is potassium a cation or an anion? Great, it's a cation. Okay, so as you can see, we have a cation and an anion. And even though H2CO3 is technically a molecular compound, when you put it in water, it actually behaves like ions. So we can visualize that maybe this hydrogen and this is going to be an anion. Let's look at this. When H and OH come together, they make water. When K and CO3 come together, they make K2CO3. So what kind of reaction is this? Thank you, Katie. This is a double replacement reaction. Put a 1 in the chat if you want to go over 5 and 6. Awesome. Let's practice with 5 and 6. So I'm going to give you guys 2 minutes to determine what are the classifications of 5 and 6. Okay, you guys. 5 and 6 have the same classification. What is that? Oh, there you go. I agree. Awesome. Great job, Maria. Great job, Vanessa. Anybody else? Double replacement. There you go. Thank you, Katie. Thank you, Elizabeth. Thank you, Isaiah. These are double replacement reactions. Questions on the classifications of reactions? Great. Let's move on to the next topic, which is oxidation reduction reactions. Oxidation reduction reactions are very important because those biomolecules that I illustrated to you guys when we learn how to calculate the nutritional calories in food, they undergo many biochemical processes or reactions in our body that are oxidation reduction reactions. So that energy that we learned earlier today actually comes from oxidation reduction reactions. Oxidation reduction reactions can also produce electrical energy, specifically in batteries. Now, one of the things that you may or may not realize is that an oxidation reduction reaction actually happened in one of the main monuments in this country, which is the Statue of Liberty. The Statue of Liberty, we traditionally know that it is green, but the formation of this green substance at the Statue of Liberty is because the Statue of Liberty is made out of copper. And that copper has been exposed to the O2 in the air, and it has made the following substance, which is copper 2 oxide. And this copper 2 oxide is this green substance, which is known as green patina, and that's why the Statue of Liberty is actually green. Now, in the process of copper being converted to copper 2 oxides and that oxygen to be converted in copper 2 copper 2 oxide, understand that what happened overall is that copper had to lose electrons in order to get oxidized, and oxygen undergoes reduction because it gained electrons on the way. So it is important to know that whenever a substance undergoes oxidation, it loses electrons. Whenever a substance gains electrons, that is called reduction. So now I'm going to teach you guys how to identify how the elements in a reactant can undergo oxidation and reduction. And in order for us to understand that, we need to know the rules for determining oxidation numbers for elements in a chemical reaction. As you can see, this is just a summary for calculation of oxidation number. First bullet point says, an element by itself has an oxidation number of 0. Okay? Now, there are elements that are diatomic. A diatomic element is an element that is found in nature with itself. So diatomic elements, which are also known as molecular elements, like O2, N2, H2, F2, Cl2, Br2, I2, also have an oxidation number of 0. Okay? So We cannot forget about the group number. If you're in group 1A, your oxidation number is +1. If you're in 2A, your oxidation number is +2. If you're a halogen, for the most part, your oxidation number is -1. You can see here that hydrogen, which when it is with non-metals, has an oxidation number of +1. But if it's with a metal, it's -1. Oxygen is going to be -2 for its oxidation number. But if this is peroxide, is -1. Fluorine is -1. The important thing to note here is that if you have a neutral compound, and as you guys can see, the following chemical reaction. How do I know that I have a neutral compound? Because you don't see a charge in the corner, okay? So on the top, you don't see a -2, a -1, so on and so forth. So every single component here is a neutral compound. So when we add the oxidation numbers for them, it must equal 0. Now, the sum of the oxidation numbers for a polyatomic ion is going to equal the charge. In the problem that I have right here, we don't have to worry about this. But let's actually use the rules that I just showed you guys to determine the oxidation number of the components of this reaction. And furthermore, understand who got oxidized and who got reduced, okay? So look at the first bullet point. An element by itself has an oxidation number of 0. So when it comes to oxidation number, in the reactant, who's going to have an oxidation number of 0? Put the symbol in the chat. Who's going to have an oxidation number of 0 in the reactant? Thank you, Kiyomi. Carbon, because it's an element by itself. In the product, who's going to have an oxidation number of 0? In the product, who's going to have an oxidation number of 0? Great job. Great job, you guys. Iron, because it's by itself. Okay. Now, Fe2O3, is that an ionic compound or a covalent compound? Put I or C in the chat. Excellent job. I love to see those eyes. It is an ionic compound. Guess what, you guys? If you have an ionic compound, when it comes to these rules, I'm just going to simplify the rules for you guys. In ionic compounds, the charge of the element equals the oxidation number. Okay. So again, in ionic compounds, the charge of the elements is going to be equal to the oxidation number. So in Fe2O3, what is the oxidation number for the iron? Let's put it in the chat. Thank you, Maria. +3. Because remember that this 3 is what used to be the charge of iron. So what is the oxidation number of oxygen? Great. -2. Questions, because I only saw one student answer in the chat. Questions about the oxidation number and the reactants? Since there are no questions, let's move on to the oxidation number for CO. Let me ask again. Is CO an ionic or covalent compound, I or C? Great. Covalent. Love to see that, you guys. So when we're trying to determine the oxidation number for a covalent compound, what we need to keep in mind is, well, since these are two nonmetals, now I'm going to approach this a little bit different. First, I'm going to assign the oxidation number of the second nonmetal. What is the oxidation number for oxygen? Look at the third bullet point on the second column. So this information. Great. Oxidation number of oxygen is going to be -2. Since we see that CO is a neutral compound, what is the oxidation number of carbon? It needs to add to -2 to get to 0. So what is the oxidation number of carbon in CO? Great job. +2. So once we have this information, understand that we have to kind of like create a little table and tell ourselves, okay, what is the transitions and oxidation numbers? And this is how I build it. I always say, well, I have iron, I have oxygen, and I have carbon. And I'm going to look at oxidation number at reactants versus oxidation number at products for those elements. So for iron is +3, and in the product is 0. For oxygen, we have a -2, in the product, -2. In carbon, it started at 0, and it changed to +2. Okay, so those are the changes. So let's put in the chat the symbol for the element that didn't change in oxidation number. Excellent. The oxygen didn't change. You know what we call an element that doesn't change? This is called an spectator ion, which is just looking at the reaction happening, looking at the exchange of electrons, but it's not playing into the exchange because its oxidation number is staying the same. Now, as you can see, we have some transition for iron and carbon. When it comes to determine who gets oxidized and who gets reduced, you guys, for me, the easier way that I have found to explain it to students is with a number line. In a number line, anything that is to the right of the 0 is a positive value. Anything to the left of the 0 is a negative value. So if you have any numbers doing this, meaning going from positives towards 0, or going from positive towards negative, or from 0 to negative, that means that that element undergoes reduction. If it's going in the different direction, meaning that it goes from negative to 0 towards something positive, or from 0 to something positive, if it goes in this direction, that is called oxidation. So when I look at what I have in this reaction, specifically reduction, who got reduced? Oh, you guys are going to do so well in this exam. Great job. Iron got reduced. So who got oxidized? Excellent job. Carbon got oxidized. Now, one last thing before I let you guys go. The way that we mention this, if it's in words, okay, you're going to say that iron at Fe2O3 is what got reduced or undergoes reduction. Because remember that the element that undergoes reduction is going to be, or oxidation, is going to be in the reactant side. So if we say, oh, the carbon in the reactant or just carbon is what undergoes oxidation, you are not going to say, oh, the carbon in carbon monoxide. That would be incorrect. So the carbon at reactant is what undergoes oxidation. Okay? Any questions about oxidation number or determining who undergoes reduction, who undergoes oxidation? Great. Since there are no more questions, thank you for coming today.